Hi, in this video, we're going to start talking about functions. Specifically, we're going to focus on the objective. Students will be able to determine whether a relation represents a function. We will do some definitions and we'll also do some practice. First, we need to know, what is a relation? Well, a relation is a correspondence between two sets. Think about a relationship outside of math. If we have a relationship between two variables, x and y, then we can say that x corresponds to y, or y depends on x. We will see that relationship written as x and then an arrow to y. Relations can be expressed in different ways. There are 4 different ways that our textbook shows relations. We'll see relations as graphs, like we have here. We have a line graphed. Y equals 3x minus 1 is the equation that goes with that relation. So we can express relations as graphs or equations. Relations could also be expressed as a set of ordered pairs. You'll see here I have set brackets, and in between those brackets I have a group of ordered pairs, each with a comma in between them. Those ordered pairs happen to all fall on the line of this graph, but note that this set of ordered pairs doesn't represent that whole graph because that graph has an infinite set of ordered pairs. But yes, a set of ordered pairs is a way to represent a relation. And lastly, we have maps. For this map here, I have my x variable on the left and my y variable on the right. And each arrow goes from an x to a y. So that is representing my relation with a map. And that map is a representation of all of the ordered pairs that I see over here. So these represent the same relation, just as the graph and the equation here are representing the same relation. Now you may be wondering, are all relations functions? In order to answer that question, we have to know, well, what is a function? If we have x and y are 2 non-empty sets, a function from x to y is a relation that associates each element of x with exactly one element of y. In this set, we would call the domain the set of all of the inputs for our function. And the range is essentially all of our outputs for the function. So if I have a domain with particular different x values, in that domain, I could also have a range or we'll say a y set. This is our set of y. We'll call this our set of x. In our set of y, we'll also have values. Each x will map to a y value. There might be other y's in the set, or other values in the set, we'll say. The ones that go from x to y there, we say that those are our range. So we have our domain here, and each item in our domain maps to an item that is in set y. And those items, those images, are called the range. Let's look at some examples. First, we have a map with the domain has names, Dave, Sandy, Maureen, and Dorothy, and the range has phone numbers. I can list that map instead as a set of ordered pairs. Let's do that. Looking at the set of ordered pairs, you can see that Dave has 1 phone number, Sandy has 1 phone number, but Maureen has 2 different phone numbers. Dorothy has one phone number. So we have to ask ourselves, does this relation represent a function? We have to say, no, it does not represent a function. Not a function. Why? Because each X input does not have exactly one output. Maureen has two outputs or two different phone numbers. Here is another map example. We have grams of fat and calories for different Wendy's items. So Wendy's single has 410 calories and 19 grams of fat. The Big Bacon Classic is 580 calories and 29 grams of fat. The Whopper is 540 calories and 24 grams of fat. The Burger King chicken sandwich is 750 calories and 23 grams of fat. The McDonald's Big Mac is 600 calories and 33 grams of fat. The McDonald's McChicken is 430 calories and 23 grams of fat. Let's write that out as ordered pairs. You can see that each X value has only one value of Y that it maps to. You might be saying, I have multiple arrows going to 23. Well, that's one of our outputs or Y values. We can have two different X values going to the same Y value. That's okay. So we can say that yes, this relation is a function. Why is it a function? Because our definition for function says that for each X in the relation, there is exactly one element of Y. Take a moment right now and look at these three examples with sets of ordered pairs. I want you to pause the video and determine whether each relation represents a function. Also, if it's a function, you're going to state the domain and the range. Pause the video and try it now, then we'll check our answers together. Right, hopefully you've had a chance to try each of these on your own. First, I'm going to determine whether the relation represents a function for part A. If it is a function, I'll state the domain and range. Now, if I'm looking to see if the set of ordered pairs is a function, that means that each X value only has exactly one unique Y value. There's no X value that has two different Y values. We have to check for that. And I can see here that 2, 3, and 2, -1. Those are both the same X with different Y values. So that means there's not a unique output for each input. So this is not a function. For the next example, I'm going to check each of my X values. I have -2, 3, 4, 1, 3, -2, and 2, -1. This is a function. I'm going to state the domain and the range. I'll put D for domain, and the domain is going to be each of the input X values, -2, 4, 3, and 2. The range is going to be each of the outputs or Y values, 3, 1, -2, and -1. Excellent. Now for part C, once again, I'm checking to see that each X value has only one unique Y value. So we have 2, 3, 4, 3, 3, 3, and 2, -1. Unfortunately, 2 has the output of 3 and also has the output of -1. So it is not a function. We can also work to determine whether equations are functions or just simply a relation. When we have equations, we need to ask ourselves, does each input X give me just one output Y? So if I have an equation like Y equals -3/2 X plus 4, I want to know, is that relation, is that equation a function or not? Well, let's think about it. If I take a value, I put in for X. If I multiply it by by -3/2, there's only one number I can get each time. That's not going to come out with multiple answers. So far, so good. If I add 4 to that, that is one answer that I can get. When I add 4 to a number, I am not going to get multiple answers. So this example is a function. Yes, we have a function. Every equation does not result in a function, though. Let's look at another example. Let's look at another equation. Here I have x equals 1/2 y squared minus 3. One thing that I can do is I can solve for y. When I solve for y, this is what I do. I have x equals 1/2, y squared minus 3. I'm going to add 3 to each side first. And I'll get x plus 3 equals 1/2 of y squared. I'm going to divide both sides by 1/2, which is the same as multiplying both sides by 2. So I'll have 2x plus 6 equals y squared. And then to get rid of the y squared, to just make it simply y and isolate that y, I'm going to square root both sides. When I square root both sides, there are 2 things that I could square to get 2x plus 6. So I have to apply a plus or minus. So what I end up with is y equals plus or minus the square root of 2x plus 6. What does that mean? Well, let me think. If I put in particular values for x, there's 2 different y values I could get out. So say I put in 1. I could get out positive, the square root of 2 times 1 plus 6. Or I could get out negative, the square root of 2 times 1 plus 6. So that's positive root 8 or negative root 8. We know that 8 is 2 times 2 times 2. So that's plus 2 root 2 or minus 2 root 2. So this equation has the point 1, 2 root 2 and 1 negative 2 root 2 as points on its graph. That is one input having 2 outputs. So this would be not a function. You can see a graph of the equation x equals 1/2 y squared plus 3, rewritten as y equals plus minus the square root of 2x plus 6. You can see here that for each of my x values in the domain, there's at least one y value. At -3, 0, there's just one y value. For -3, it's just the output 0. But for every other input in the domain, there are 2 different outputs. And we're going to learn about something later on called the vertical line test. And you can see here that a vertical line can be drawn through 2 different parts of the equation right here. So this is not a function, but we'll explore this property more in another section. All right, now you should be prepared to move on to the next topic in section 1.1.